This is a two-part presentation because there's just too much information to fit into 1 hour. And I'm going to work really hard to keep this in 1 hour because it's a lot of material. But I think you'll find it interesting. And I certainly do. It's been my passion for many, many years. And I will say that Doug, who was just speaking a few minutes ago, is the one that prodded me into putting this presentation together years ago, kind of uh, archiving my discoveries and the things that I've done over the years. So I had a lot of fun putting this together. And what you'll find out is a lot of the material that's in here, a lot of the photographs are things that I either own or have owned. So that's one of the things that I thought was really kind of cool about this presentation. So let's start. We'll talk about what this talk is not about. Okay, we're not going to debate about who's got the best receiver. Yeah, each of us knows who has the best receiver. I certainly do, but we're not going to debate that, and because it's really a matter of personal opinion. And I really won't give any recommendations on any of that either. And I won't try to bash any particular receiver unless it really deserves it. And there are a few of those, as you know. And I've given everybody the leeway of inserting a photo of your favorite turkey right there. I will add a disclaimer, as I just said, that the opinions expressed herein are strictly my own. You may disagree with me, and that's perfectly okay. There's nothing wrong with that. So there. What we will be talking about is things like who actually built the first receiver, the first radio receiver. We're going to break this down into what I call the defining moments in receiver development. We're going to talk about the things that make a good receiver. What makes a good receiver that we want to use? We'll talk a little bit about Armstrong, but he wasn't the CEO of AT&T. Well, he was the CEO of AT&T, but he was a different Armstrong. This is a guy that I used to work for at Hughes Aircraft. This part one will cover the first 75 years up to about World War II. So it's going to start in the 1800s and it'll end just prior to World War II. And the next part two, will introduce the technology of World War II and go from there up to current state of the art. So a little bit about me. Those of you that don't know me, I am an obsessed radio collector, and I tend to. Yeah, but Lisa's smiling over here and chuckling. She knows me. If you saw my shack, you'd know. Um, I try to get radios that are, to me, are of technological importance. In other words, they they really made an impact and made a difference in the way that things are done, the design and engineering of the radios. This all started for me in the 1960s. I'm still doing it. I've never stopped. And along the way, I've learned quite a bit. And I'm just fascinated. I love the history aspect of this. This is the key to this is I'm fascinated by the history and I'm I wish I was born 50 or 60 years earlier to have been part of what took place in this presentation. Because there's just some amazing things that were amazing discoveries and creations of that time. And of course, I'm still looking for new additions all the time, and we're still adding to it. Okay, so I said we're going to talk about what makes a good receiver. Well, it really depends on the application that you're trying to do. I mean, a good receiver might be used for a cell phone. It might be used for communications like amateur radio. It might be used for radio astronomy, satellite telemetry, other things we don't know. We're going to focus on communications receivers here. One of the things you want to be able to do in a good communications receiver is detect signals down to the noise floor. That's minimum discernible signal, MDS. That's what you want to be able to receive. You want to be able to withstand strong nearby signals. In other words, strong transmitters that are close by, like the fact that I can operate 3 HF radios simultaneously in my shack here on different bands. I want to be able to reject those other stations. So a good receiver has to be able to do that. I also want to have a wide dynamic range in a good receiver so that I can detect those weak signals as well as the strong signals and not be overwhelmed by that, but also have a good range for being able to receive the signals. And I want to be able to hear that signal that I'm interested in. That's the most important part. I don't want it to be obscured by other things, noise, QRM interference, and what have you. I want to have stability and tuning and resetability. These are two really important things in a radio. It might surprise you to hear that these definitions were written in 1932 by James Lamb. James Lamb was editor at QST with the ARRL. I think he was the technical editor for QST, and he defined what makes a good communications receiver in 1932. So that's kind of interesting. Things have not changed. And he did a good job of defining it. And we'll talk more about what he's done in later on in the presentation. So this all starts in 1861. So we're going back quite a ways. This guy, James Clerk Maxwell, you guys have heard of him. James Clerk Maxwell publishes an article, a paper on the physical lines of force. And what he basically expresses is that electricity and magnetism are manifestations of the same phenomena of an electromagnetic field. And of course, those are Maxwell's equations right there. And this has been termed the second great unification in physics, was what Maxwell came up with. Now, the problem in 1861, he could theorize this, but there was no way to prove it. There was really no way to prove that. So what he did was actually based on the work of many others. And I will say, if you think about the history of radio and communications, this is exactly what it is. We build on the shoulders of those who came before us. So no one single individual is responsible, but many individuals have contributed to where we are today. And that's an important part of it. But if you think about the other guys that were the other scientists that were working back then, the physicists, you got Faraday, who was dealing with electromagnetic induction, Oersted with the electromagnetic field. You've got Henry, who postulated electromagnetic waves, and Zantadeschi, I can never pronounce his name, Zantadeschi. He suggests a connection between light, electricity, and magnetism. Of course, we know today that's true. But Maxwell put all this stuff together and created this paper on physical lines of force. But there were others involved back then. Let's talk about this guy, William Henry Ward. He is interesting guy. I get a kick out of this. He was awarded a patent in 1872 for a thing called a method of collecting natural electricity. Well, it kind of sounds like a receiver, right? Kind of sounds like that. Well, it has no basis in scientific fact. But if you look at the patent, if you go explore that patent number, it's got some really cool drawings in it. That's what I like about it. I'll show you that drawing in a second. It has a nice drawing in it. So this guy, you never hear about this guy. The next guy, you probably have heard of this guy, Millen Loomis, in 1872. He also received a patent, wireless telegraph. But not like Ward, he didn't have any fancy drawings or explanations. But anyway, we don't get to see any of that stuff. And today we say, this really wasn't electromagnetic radiation. It was really magnetic induction is what he did with his wireless telegraph. So it really wasn't a radio. Neither one of these systems is capable of reception or emanating electromagnetic waves. So they don't count. But here's the picture of Ward's device. It looks kind of cool. It looks like a still, actually, to me. But anyway, so the first defining moment that the first one I want to define is proof of Maxwell's work. And that was done by Heinrich Hertz in 1887. He proved that Maxwell was correct. He built an apparatus and he was able to transmit electromagnetic waves from a transmitter to a receiver. Now, it was a simple system. It consisted of what we would call a spark coil, a Runcorf coil. This is the proper name of a spark coil, and that's, you can see. Let's see. Let me get my laser pointer up here. You can see the spark coil, of course, right here. You've got an interrupter, a capacitor, a spark gap, and this is actually a dipole antenna, and the receiver is just a loop antenna. So you see the pieces he has here: the Rumkopf coil, a tuned dipole, a receiving dipole. And what he was able to do was create a spark across this gap, which proved that he was actually emanating electromagnetic waves that were being picked up by this coil and going across the gap here. So he published in 1893 this paper, Electric Waves Being Researches, and that's interesting English, but being researches on the propagation of electric action with finite velocity through space. I think that's probably a translation from the German, but I'm not sure. Anyway, this was really a defining moment in radio communications. This is the proof that really existed. We take this for granted today. So the next guys that come along are Branly and Lodge. Now, Edward Branly, he comes up with a gadget called a radio conductor. And there's a little picture. I got a bigger picture that I'll show you in a second. This is a device known as a coherer. And if you know anything about early radio transmission, the coherer was used as a receiving device. He was noticing how dust behaved in a flour mill. If there was any electric charge, the dust would collect and stick together. Well, with the right combination of metals in an evacuated metal vial like you see here, if this was exposed to an electromagnetic field, the metal particles inside would cohere and it would conduct electricity. And if you remove the field, they still stay stuck together. They still cohere. So if it receives an electromagnetic signal, the particles stick together, they conduct electricity, and you can do something with that, like ring a buzzer or whatever you want to do with it. When the field goes away, it's still conducting. So what you have to do is you have to tap the vial to knock the metal particles apart, and then it'll stop conducting. So that was the coherer. Like I say, they still cohere, but by tapping the vial, and you'd use a pencil or something and just pop the vial and it would stop conducting. So Lodge called that the coherer. And it basically, they added a simple, like a bell or a ringer that taps the vial. So as soon as it starts conducting, it's a feedback. So the thing starts conducting, the bell starts clapping against the vial, and that's known as a decoherer. And now, with that little addition, we can respond to Morse code very easily. But there's a guy that is overlooked, and I have to bring him up, and his name is Popov. He is a Russian, Alexander Stepanovich Popov. In my mind, he actually built the first practical receiver, and it was in 1894, and it was used to detect lightning. Of course, what is lightning? Lightning generates massive amounts of electromagnetic waves. He built a receiver that actually was a warning system for approaching lightning. And that was in 1894. And I consider that the first practical receiver ever. Predates a lot of other stuff we'll talk about. But he used the Branly coherer to do that, which makes sense. He refused to patent it. He wasn't interested in the financial gain of this thing. But a lot of others were doing experiments at the same time. And you know who some of those, you'll recognize those names. But he wasn't interested in the financial gains of this. So he played around with it, and he actually built an early wireless system, but it was not very practical. But the receiver itself was a practical receiver. So here's what a coherer looks like up a little bit closer. You can see the glass vial and the two pieces of brass here and the little metal filings in between there. And you can hook this up to an antenna. And actually, I actually use that to do a demonstration. I have a really nice transmitting coil. It's a low power transmitting coil, and I set this up as a receiver and demonstrate that we can actually transmit Morse code and receive it with this little coherer, which is kind of cool. So a couple of names, one name at least that most people are familiar with, Tesla, and we'll talk about Bose. Bose is one that was overlooked until just recently in the last few decades. But in 1893, Tesla actually publicly demonstrated a wireless system. He described the method. So he defined what it took to build a wireless system. And in the year 1900, he received 2 key US patents on wireless. Interesting. So he received those patents on wireless. But in 1894, a fellow by the name of Bose, Jagdish Chandra Bose, who is not related to Bose speakers, by the way, it is a different Bose, but he actually built a system kind of like what Hertz did, but he was actually publicly demonstrating radio waves, radio transmission in his home in Calcutta. He traveled to London and visited with Guglielmo Marconi in 1896. Interesting point there. So now Marconi is getting some information, and that created just a huge flurry. I think Bose was actually a speaker at one of the I can't think of what it's called, the convention that they had. It was like a physics convention, and he was a speaker there, and that's where Marconi met him in 1896. And of course, the rest is history from there. We'll talk about that history. But this caused a flurry of interest in wireless. So it's interesting that Bose was not recognized until the 80s, the 1980s, late 80s, was recognized that he was really doing things in the late 1800s that predated a lot of the other things that these guys were doing, like Marconi and like Tesla and others. He really came up with something. The interesting part of what he was doing was the spark generator that he used in his experiments. We believe from the physical size of it that it was actually radiating up in microwave frequencies, not down in the low kilohertz range like a lot of the spark systems do. He was actually working up in the very short wavelengths. One of the things that he did understand was polarization of radio waves. That was one of the things that he was able to detect and show in his experiments. So he doesn't get credit with that, but he's the guy that found that. So as a result of all this flurry of interest, Marconi in 1896 gets his own patent, and that's it right there, 12039, British patent. And that's considered by many the initial patent for radio. Well, technically it wasn't, but this was the initial patent in Britain, and it was based on the work of Tesla, Branly, and of course Bose, all of these guys. That's what he based his work on. So Marconi, let's talk about Marconi. I have a great deal of respect for Guglielmo Marconi, even though he didn't really invent anything. Everybody likes to think of him as the inventor of radio. He isn't. He was an entrepreneur, a very, very well-educated entrepreneur, had lots of money, and was able to do a lot of experimenting. And he built his business on existing ideas and the apparatus of others. So this guy built an empire, a communications wireless network based on the things that he learned from other people. So he didn't really invent wireless. He just made it a money-making opportunity. So I have a lot of respect for what he did because he understood the things that he drew from to build something bigger, but not invent anything. So he improved on those existing ideas in the apparatus, and he saw that as a business opportunity for communication. And Marconi, of course, is considered with being the developer of the first practical wireless telegraphy. So he worked on improvements of that Branly Lodge Coherer decoherer, and he built really big Rumkopf transmitting coils. I mean, really big. We're talking kilowatts of energy, their power, really big transmitting coils. And he built a series of wireless stations and was able to transmit messages. And on 17th of December in 1902, the guys at the other end knew what they were listening for. So they were kind of primed, and we don't really know that it really worked. There's a belief in looking back at things like the solar cycles at the time that this took place, that since it's a spark system, there are lots of harmonics off of a spark transmitter. They actually might have received some of the signals across the Atlantic, but they would have been at much higher frequencies than what they thought they were operating at, which is kind of curious. But they've tried to reenact. This has been reenacted on occasion. You may have read about that in QST, of course, on the anniversary in December. It's a big deal. In 2002, there was a huge reenactment of that really was great. But the one thing it did do is it did earn him a Nobel Prize in physics in 1909, and he shared that with another gentleman by the name of Carl Braun. And we all are familiar with this thing, a crystal detector. Carl Braun came up with a crystal detector. So that was an improvement on the coherer. Okay.
Dennis,
Yes, sir.
I was going to add a little something.
Hey, Doug, why don't you hold it till we're done? Rather
Okay,
than, yeah.
but it fits right now.
Okay.
On a trip between Florence and Bologna, Italy, we stopped at Marconi's house, which
Yeah.
is now a museum,
Yes.
and I stood in the window and looked out at the hill. I also got to operate 6 different decades of radios in the place where they had them set out. So if you go on your way to Florence, stop at Marconi's house. It is a mind-expanding experience.
Yeah, that would be cool.
Yeah.
That would be
Okay.
nice.
Thank
All right,
you.
Doug, thanks. Um, in 1903, the one thing we're most familiar with from the early crystal sets and the crystal detectors was a thing called a cat whisker, and that was developed in 1903 by a fellow by the name of Picard. He patented the cat whisker detector. So that's really like a galena crystal with a cat, what they call a cat whisker, or a little wire touching it. Of course, you have to find the sweet spot on the crystal for that to work. But that was an important discovery that really created a flurry of crystal sets, easier to build, and people were able to build their own receivers at that point. Well, the battles between Tesla and Marconi, we're all familiar with a lot of that. What ended up happening is that the U.S. Patent Office overturned Tesla's 1900 patent, and they made Marconi officially the creator of wireless, which was, I am Dennis's opinion, Tesla was robbed, and it was that'll prove out in the next years to come after this that he was robbed. So he pursued this. He went to the Supreme Court and pursuing with a lawsuit. And in 1943, the Supreme Court revoked Marconi's claim. The sad part of this is that Tesla died 2 months before that decision. So Tesla's original patents were reinstated, and it's kind of interesting. We've got some theories, and again, I'm going to talk about some theories about why this happened. I don't know the veracity of this, but there are several theories as to why the courts revoked Marconi's claim. One was it allows the government to avoid paying damages to Marconi for use of the patents during World War I. And I think that's an important one. That could have a lot to do with why they were overturned. And they originally gave the patent to Marconi to avoid Tesla's claims. So they were kind of, maybe the government was being a little fishy and trying to skirt what was going on. But anyway, needless to say, Tesla's patents were reinstated, and today we know Tesla is officially, the creator of what we consider wireless. So we got to start improving on these receivers. These coherers and things don't really work very well. So cat whiskers, we'll talk about some of the early receiver. These are some of the components. Galena cat's whisker. That's a pretty common device. I remember as a kid building a receiver with one of those. And this is one out of my collection. Both of those are out of my collection. An electrolytic detector. So it's a chemical detector rather than using a crystal. Some of the other parts of early sets, there's an early crystal set. That's this guy here. The loose coupler, which allows us to tune the radio. That's what the loose coupler is. And of course, this is what they call an opera crystal set. So it's a little personal crystal set that you can hook your headphones up to and listen. That's kind of a cute little one. I like that. But basically, the technology remains unchanged. This was the technology of the day until about 1906, which leads us to our second defining moment. Something new is needed. So the performance is limited. The crystal detectors you need a really, really strong signal to get any performance out of it. And that's difficult. Marconi used a galvanometer as an indicator. You weren't sitting there with a pair of headphones listening to Morse code. He was using actually an instrument that, a galvanometer, basically a voltmeter and I believe, I may be mistaken, but I believe he was using what is called an optical galvanometer, which has a mirror and a light source, and it actually moves when the needle moves in the galvanometer, the light moves, be projected against a wall, and you can see the thing move, and that's how you copy the code. Well, that's kind of cumbersome, and it's not very sensitive. It's a real challenge. But along comes a guy by the name of John Ambrose Fleming. You've probably heard this term before. He worked for Marconi, and he was helping Marconi build his transmitters, those big, giant spark coils. Well, in 1904, he applied for a U.S. patent on something called an oscillation valve. Well, valve, that's a tube, right? Vacuum tube. We know that term, valve. Oscillation valve. Well, that's a little misnomer. But if you think about this term, this is what we know today as a vacuum tube rectifier. This was a big deal. So here's his patent, and this is really a game changer, and it really improves the sensitivity of the receivers. It's based on what's called the Edison effect. Edison's laboratory, I won't say Edison himself, but I'll say his laboratory discovered something called the Edison effect. It says when you heat up a filament in a evacuated container, and you add a plate, well and put a charge in there, that filament that's heated up will emanate electrons. They'll emanate from there. But he saw no practical use for that. He is okay. What are we going to do with that? He didn't have any idea. Well, Fleming figured out what to do with it. So he takes a filament, a light bulb, adds a plate, and now he's got the oscillation valve. So with Marconi, he's using that with a coherer and that valve, that rectifier, with a galvanometer, and is significantly more sensitive than it was before. Much greater reliability. It's a much more reliable system. And we consider that the first vacuum tube. That's what that was. And here's a picture of the patent. And you can see this is his envelope, the glass envelope. And there's a plate and a filament. And he's showing a charge on here and as a receiver. This is actually an antenna. And there's the galvanometer right there. So it's interesting. And he's showing them in parallel down here to get greater sensitivity. So that was an interesting development. Well, what came out of this was another guy, and I hate to say it, this guy was a real charlatan, but he is credited with coming up with something very important, and that's the audion. This guy, Lee DeForest, 1906, he creates something called the triode. We all know what a triode is. Well, if you know vacuum tubes, you know what a triode is. Well, he took Fleming's design and added a grid in between the filament and the plate, and realized that he could put a charge on that and control the flow of electrons between those two. And he called that a modulation grid. That's what he called it. So now he's got a device that'll detect. So it can detect radio signals, it can amplify radio signals, and it'll also oscillate. So he's granted a patent on this thing. He actually got a patent on it in 1908. And he was in litigation. He and Fleming were in lawsuits until 1943. But what's interesting is Fleming's patent was declared invalid, and I find that really upsetting personally. That should not have happened. But anyway, the thing about, we'll talk a little bit more about DeForest. He was a bit of a a charlatan. Anyway, this is a 1906 audion. This is like, you consider this our first vacuum tube triode. And this is not mine. This is, I can't remember where this one's on display, but I do have an audio, and I should have brought that with me out here. You could have seen it. I've actually got one in my collection, an audion, which is really kind of neat to see that. Anyway, Lee DeForest, this guy, we'd call it a tinkerer, right? He was a DIYer, and he had no clue how this thing worked. He had no clue at all how this triode that he created worked, the audion. No idea. He tried to explain it off and saying, well, there's ions in there, and that's what's causing it to work. It's a ion. There's no gas ions in a vacuum. It's an evacuated tube. So he really didn't know how the thing worked. He was just tinkering around and discovered something. So I give him credit for discovering that. They really did not work very well. They were really, really bad tubes. But it did create a revolution. You have to say that. Eventually, many years later, and this is many, many years later, Irving Langmuir of General Electric was able to describe how the triode worked. So it took a long time. Nobody really understood it. So DeForest certainly didn't, but Langmuir figured it out. So we now understand how they work. But DeForest, we can give credit to DeForest for one thing. He coined the term radio, which we common use today. So we give him credit for having come up with that term radio, which is pretty cool. And he also created the first public radio broadcast, which is kind of neat. And that was on January 12th, 1910. And it was billed as a public broadcast, so it advertised and what have you. And it was from the Metropolitan Opera House in New York City. It was Tosca. So that was the first public radio transmission. DeForest made some radios. I've got some of his stuff, D10, which was an interesting receiver. It's called a reflex receiver with 4 RF stages and a crystal detector. So it's using that earlier technology. By this time, when this receiver came out, the vacuum tubes were a little bit more sophisticated than the than the audion, but it consisted of a crystal detector with 4 audio amplifiers after it. So, and that's I've actually got 2 of these now. That's what it looks like. The other part of that is he had this great idea of a small antenna like that. Well, that did not work. That little antenna, that loop antenna that you see there, waste of time, never worked right. But that's the D10 DeForest receiver right there. Well, what came along after this that started really improving things? Now that we had a triode, we could actually amplify the RF signal. And so what we came up with was something called a tuned RF receiver, or a TRF, and these were quite popular and very commonplace back in the late teens, early 20s, 1920s. The triode provides a lot of gain. Well, it provides some gain. One is good, so more have got to be better. So these guys started chaining RF amplifiers together. Well, that leads to more problems, but yeah, more is better. More stages lead to, you guessed it, instability. It's prone to oscillation, but there were a great many TRF receivers, and they were difficult to tune because each stage had to be tuned individually. They weren't ganged together. You had to tune each one and peak each one up. And here's a very typical example of a TRF receiver. This is one that I had in my collection that I got rid of some years ago. But it's an Atwater-Kent Model 10A. That was one of Atwater-Kent's earliest receivers. And it consists of 3 RF stages. There's a tuned circuit here with an RF amplifier, another tuned circuit, RF amplifier, another tuned circuit with an RF amplifier. There's a detector and an audio amplifier. So that is the 10A right there. So that was but it is difficult. I can attest to the fact it's difficult to tune this thing in to get, and there were only about, in all the time I had that receiver, I only ever picked up 2 stations with it, and one was only a few miles away. So it tells you a lot about it. But it was, these were very popular. There were a lot of them made. But along was Ernst Alexanderson. I'll mention Alexanderson. Some of you may have heard this name before in a different context, but he was really the developer of that TRF when he was at GE. He was working at GE in 1916, General Electric. So he came up with this idea of stacking all these stages together. So the positives of this, these are good. It's good sensitivity. By nature, it has high Q with all those tuned circuits, so it's very selective, which is important. And the tubes are inexpensive. They're inexpensive triodes. So, it makes for a very inexpensive receiver. But there are drawbacks. Like I said, it's difficult to operate. They're unstable. They're tough to tune. But a lot of TRFs were built by a great many companies. In fact, a lot of them were home built. People were building these themselves. I should mention Alexanderson is most commonly known for the development of what was called the Alexanderson alternator, which was a replacement to the Rumkopf coil, spark coil. This was a continuous wave generator that was electromechanical. So it had a motor that turned a generator that generated an RF signal that was a pure sine wave. And so it was a continuous wave transmitter. And there is one of these, if you've heard of this, it's on the air in Sweden. They put it on the air every once in a while. It still operates. It's the Alexanderson alternator at radio station SAQ. If you're interested in that, look up information on SAQ in Sweden, and there's a wealth of information. I'm a member of what's called the Alexander Society and have friends that actually have gone and operated the station there, which is to me just fascinating. It's a beautiful, beautiful piece of equipment. These were very common. Marconi used a lot of the Alexanderson alternators, but they were overcome very soon by other systems. But anyway, that was what Alexanderson was known for. So I'm going to start talking about what comes next. Number 4, defining moment. This is an important one, the Heterodyne principle. The Heterodyne principle was originated by Reginald Fessenden, or Fessenden. You've probably heard that name too. He's got a lot of things to his name, but Fessenden came up with this idea of the Heterodyne, and he proposed this in 1901. Of course, the problem in 1901 was there was no technology to be able to do it. He theorized that you could take 2 frequencies and mix them together and get the sum and difference. That's the Heterodyne principle, but you couldn't prove it. He had no way to prove it in 1901. So that's what we talk about. F1 and F2, frequency 1 and frequency 2 get mixed. You get the sum and difference of those 2 frequencies. What he needed to make that happen was the triode. And so when the triode showed up 5 years later, um, they came up with that they were able to demonstrate the heterodyne. But one of the things that Fessenden is known for, and I find this really amusing, is that he took, well, I'll tell you, he was credited with the first voice broadcast by radio. And it was from Brant Rock in Massachusetts. And what did he use? An Alexanderson alternator from GE. It was a 500-watt alternator that transmitted at 75 kilocycles. And he figured out a way to modulate that. He put a transformer in the output and drove that with a microphone. Not very smart. I mean, you're dealing with high voltage. You know, it probably burned his lips a little, I'm sure. And on Christmas Eve, before DeForest was transmitting, on Christmas Eve, 1906, he was transmitting music and talking. Now, what's funny is if you read the accounts of this, go to Wikipedia and read about Fessenden and his broadcast in 1906. They'll tell you it was heard in the Caribbean. It was heard in Jamaica. Not really. It was heard in Jamaica, New York, which was about 200 miles away. I get a kick out of that. But they talk about it was heard as far away as the Caribbean. Anyway, it was heard in Jamaica, New York. So 200 miles. I mean, that's nothing to kid about. I mean, that's a good distance. 1906, transmitting to a station 200 miles or transmitting to a receiver 200 miles away is really great. So let's talk about the next guy to come along. He's one of my favorites, is Edwin Armstrong. This man was brilliant. He was a prolific inventor that put all of this stuff together. He's the one that made all of this stuff play together. In 1914, he comes up and invents the concept of what we call a regenerative receiver. He was an undergraduate student at Columbia University. He patents the concept and it becomes a windfall for him. The regenerative receiver became the standard at that time in that age, in the mid-teens. He took an audion vacuum tube, a triode, added positive feedback to that audion, got it to oscillate, but it's not quite at oscillation. It's just on the verge of oscillation, which is where the regeneration comes from. When it's on the verge of oscillation, it becomes an incredible amplifier. And so it's able to detect extremely sensitive signals. So this is the schematic of his regenerative receiver. And the positive feedback comes from this coil right here, L3. In 1917, Armstrong joined the Army. World War I, the Great War is taking place. He joins the Army and he joins the Signal Corps. And one of the amazing things that he did, he gives free use of the patents to the Signal Corps, to the government. And so we were able to build receivers without any licensing or anything from Armstrong for the use of these receivers during the war, which was important. So this idea that you can add feedback to an audio and it will basically cause that tube to amplify. If you're just on the verge of feedback, on a verge of oscillation, it will create a great deal of amplification. And I know probably a few of you out there have built regenerative receivers or have them. I've built a few over the years from the time I was a kid, and they're pretty cool. And they're kind of touchy. You got to play with them, but they're fun to play with and they're easy to build. So what comes out of this, of course, is the next defining moment, the regenerative detector. This was patented in 1914. There's the patent number. And it's about this positive feedback applied to an amplifier. And if you apply too much, it oscillates. If it's just right, you get a lot of gain. And that's the regenerative detector. And that's Armstrong. We credit Armstrong with that really was, to me, a defining moment in radio. It frees us from headphones. We can now use a speaker, a loudspeaker. The whole family can sit around the radio and listen. It'll drive a loudspeaker. We had to use headphones up to that point. The other thing that's interesting about this, since we're talking about receivers, but since it oscillates, it's also a transmitter, of course. So this is good in some instances, and in other instances, it's bad. We really don't want that to happen. Can you imagine living in a high-rise apartment building and everybody in that apartment building has a regenerative receiver? And they all have a little bit too much feedback. They're all oscillating and they're all interfering with each other. You're hearing heterodynes from everybody. So anyway, that's an interesting thing. But anyway, the regenerative receiver was a Huge thing. This led, of course, to the patent wars. What happens? RCA licensed the regenerative patent from Armstrong. And there it is right there. This is actually an RCA from an RCA regenerative receiver that I have. Um, they licensed the patent, but there were a lot of manufacturers out there, and this led to, like I say, the patent wars between these various companies. What ended up happening was that I'll talk about some of the other manufacturers and show you Westinghouse. Westinghouse actually manufactured radios for RCA, and Crosley did the same thing. It's manufactured by Crosley, but this is under the Armstrong patent, which was owned by RCA at the time. So what a mess. This was a big mess. How do you get around that? You know, everybody was building these radios, and they had to license them from RCA and Armstrong. So other regen sets, I've got a couple others here. That's a Westinghouse Areola Senior, and I've also got to go with that. There's a two-stage audio amplifier that goes with that, which is really cool. And the Westinghouse RADA, it's RF amplifier, detector amplifier. I've got a couple of those in my collection, which are kind of cool. It's a neat little receiver. Other regenerative receivers, the Radiola 3, have a few of those in my collection. And this particular Crosley is one I'm extremely proud of. Crosley, interesting guy. This Model 51, I picked that up off of eBay many years ago. It was brand new in the box. It had never, ever been used. And so that's a radio from the early 20s. Think about it. That is brand new old stock Crosley 51. So I think that's really cool. Of course, we built a lot of regenerative receivers were homebrewed. A lot of us built those. There's an example of a beautiful homebrewed regenerative receiver. This one was built from an article from George Grammer in 1932 QST called the Rationalized Autodyne. Autodyne is another term used for a regenerative receiver. It's also used, those of you who are into QRP and direct conversion, Autodyne, that's what that is. Autodyne is a direct conversion receiver. This is another one I've got in my collection that I think is kind of cool, is the 1-2 Boy Scout regenerative receiver. This was built in 2001 by a fellow by the name of Todd Warr. It was on eBay, and I saw it. I had to have it because it's just so beautifully done. But it's built to the design from the Hammerland Shortwave Manual from 1937, which I have a copy of to go with it. And he did a beautiful job on that. It's really nice, and it works. So let's continue on with some of Armstrong's accomplishments. In 1918, he's working at the Signal Corps lab, and what does he come up with? Based on Fessenden's Heterodyne principle, he comes up with the first Superheterodyne receiver. He bases that on the Heterodyne receiver. So he uses an audion as a local oscillator. We know that term today, a local oscillator. It uses a lower intermediate frequency. So you mix the incoming signal with the local oscillator, convert it down to a lower frequency. And by converting it down to a lower frequency, it's easier to obtain high gain and high Q, which means higher selectivity and higher gain, which is great. So the Superhet is really a huge improvement. So it's also more stable, which is another important part. So this is, in my mind, this is defining moment number 6, the first Superhet. And here's a photograph of the first Superhet. And I think this is not the original. Yeah, this is located at Fort Monmouth, which Fort Monmouth is no longer there. That used to be the Signal Corps laboratory was at Fort Monmouth, but that's been shut down. This is not original, but it's the reproduction of it. But his second set is actually, the second one he built is actually on display at the Smithsonian. And I think it's kind of cool. That is on display at the Smithsonian. Like I said, this principle of this receiver right here is still used today. A lot of you have receivers that are based on this, and it looks like this. You've got an RF amplifier, a local oscillator with a mixer. You go through a filter and an IF amplifier. You demodulate it and amplify it out to a speaker or whatever. This is so common and widespread today. We all use this. This was a really important invention, creation on the part of Armstrong. But now we got more patent woes. In 1928, he loses a patent on the Superhet. There was a French patent that claimed 2 years prior to Armstrong that was in France by Levy. And so the US Patent Office doesn't like to rock the boat. They don't like to create interference, so they pulled the patent away from him. So instead of continuing on down that path, he decides to go and develop FM, right? We know Armstrong came up with FM. He developed the concept in the 1920s, but it wasn't until the 30s, 1933, 1934, that he was able to create a practical system for FM and was awarded that patent in 1933. And so in 1937, he started the first FM radio transmissions from W2XMN. Now that looks like an amateur radio call, right? Back in those days, uh, these calls were experimental. That X, you wouldn't see a ham call, an amateur radio station with an X in the call like that as the first digit of the suffix. This was an experimental license, W2XMN. And now Armstrong and RCA get into their patent war. And RCA really came out on top at the beginning, but Armstrong fought and eventually overcame the RCA patents. But unfortunately, it's a repeat of Tesla. You know, Armstrong in 1954, he dies penniless, just like Tesla. You know, Tesla got nothing from all of his efforts. So really sad because Armstrong was really a brilliant man and really came up with a lot of great things. But anyway, the first superhets started appearing in the early 20s. And again, this is one out of my collection. This was built by Western Electric. It's a Model 4D, and there's some photographs of it. This is a superhet. Now, what this was, if you go back and look in the old Western Electric documentation, this was actually a station monitor. The civil, oh, what did they call it back there? It was not the FCC. It was the civil whatever they called it back in those days. Anyway, just like today, you're required to monitor, if you're a commercial broadcast station, you're required to monitor your signal. Now, Western Electric was big into broadcast transmitters in those days. And they supplied that the transmitters were leased. You didn't own it. The receivers were part of that system. And this was for monitoring your signal off the air. That's what this receiver was for. So if a station had a leased Western Electric transmitter, they probably had one of these receivers as well. And I ended up with one of these in my collection. It's quite fascinating little piece of equipment. But like I said, as you know, the superhets would eventually rule. They really do away with all the problems of all the previous stuff, the TRFs and the regeneratives and all that. But they're expensive. That's the problem. They're expensive. Very costly to build. And the drawbacks of the superhet, like I say, it is expensive. In those days, it was expensive to build one of those. And the TRFs were so cheap, they were really the receiver that everybody wanted to use, was the tuned RF receiver. Now, as I mentioned before, the TRF had a lot of problems: instability, oscillation, hard to tune, resettability was a big deal. So here comes this guy, Louis Hazeltine, in 1922. Triodes were unstable. That was the problem. It was an unstable device. So this was caused by what's called interelectrode capacitance in the triode. So he comes up with a way to neutralize that capacitance. You've heard about neutralizing a PA and a power amplifier and a transmitter. That's what we're talking about. He uses a little bit of capacitance to neutralize that, in other words, cancel out that interelectrode capacitance. And he comes up with something called the Neutrodyne. And now you can take a TRF, neutralize the RF stages, and it becomes a stable, easy to tune, very rugged set. And this was really, it's still less costly than a superhet because it requires more components. It's a little bit more expensive than a TRF, but it's a lot better than a TRF. So these things became very, very popular. One of the big things about it, of course, it doesn't transmit. Unlike a regenerative receiver, it doesn't transmit, which is good. And what came out of that was something of the formation of what was called the Independent Radio Manufacturers Association. This was a group of manufacturers that got together to produce these Neutrodynes. And here are some examples of Neutrodyne receivers. This is from Amrad. This is a beautiful set. And there you can see there's the neutralizing capacitor right there. It's a little capacitor in each stage in this receiver. This is a three-stage TRF. Another one is a Fried Eismann that I have. This is a Fried Eismann NR5. And in here, there's the neutralizing capacitor. It's like what we call a piston capacitor today. That's the neutralization capacitor right there. And let's see, moving on, I've got one that was home built. This one is just gorgeous. This is a gorgeous receiver, really well-made Neutrodyne, beautifully done, and a real nice find for me. Now, all this time, we're still fighting the RCA patents for the Regen set. The Regen sets are still inexpensive. They're high performance, but you still have to pay a patent fee back to RCA. So how do we get around that? Defining moment number 7. And this leads to a big, big thing. Two fellas by the name of Browning and Drake. And it's not Drake that you think of today of R.L. Drake, the ham radios. This is a different Drake, not related. But these guys are two undergrad engineering students at Harvard. They came up with a better regenerative set that didn't interfere with the RCA patent. They came up with a way to build something called a Regenaformer. The Regenaformer did not violate the RCA patents. So all of a sudden, we've got a regenerative receiver that we can build and not have to pay any license fees to RCA, which is great, the Regenaformer. So rather than using capacitive feedback like you saw a typical regenerative receiver uses capacitive feedback, it uses a loosely coupled coil for the feedback, and you control the feedback with that coil. But they needed somebody to make some parts for them. They were just a couple of engineering students. They want to produce these things and sell them and market them, but they don't have anybody to do it. Well, there's a company where they were, where's Harvard? In Massachusetts, in Malden, Massachusetts, there's a little company there called the National Toy Company, located in Malden. Now, the National Toy Company was doing just that. They were making toys. And they were approached by a manufacturer's representative by the name of George Hill from Cardwell. Cardwell was a manufacturer of variable capacitors. He was selling so many of these, the Cardwell couldn't keep up with him. So he goes to National Toy Company and says, hey, can you make these for me? And they say, sure, we can make those. They're just made out of metal. We'll just stamp them out and we can make those for you. So National Toy Company got into the business of making variable capacitors. So are variable condensers in the terminology of the day. They were contacted by Browning Drake to make variable condensers and Regenaformers. So they started manufacturing this stuff. Here's a name you may recognize. If you've been around radio for a while, if you're an old timer, Velvet Verniers. National Toy Company made Velvet Verniers. Well, we know them now, or knew them as the National Company in 1916. And they had quite a legacy. National has an incredible legacy of receivers that they built over the years. We'll talk about some of those here and in the next presentation. But National Company, they figured out a way to circumvent the Armstrong patent. National took Browning Drake's parts and put them into a kit. Okay. So you buy the kit and build it yourself, and you no longer owe money to RCA for the regenerative receiver. This is beautiful. And Browning and Drake, as well as National, were not manufacturing radios. They were just making radio parts and selling them to tinkerers to build their own. Great way to get around the patent. But National establishes a company just to assemble the radios. The company would buy the kits, assemble the radios, and then sell them. So they got around the patent that way. It really doesn't infringe on the patent anyway because of the way that they produce the feedback. But the National's company buys the radios, they put them together, and then they sell them. And they're not encumbered by the Armstrong RCA patent, which is wonderful. And of course, this sets, if you've heard of National Radio Company, this sets the course for their future. And here's a really nice example of a Browning Drake. And many of these, some of them are commercially made. Some of them are made by guys like you and I, just building them in the garage out of kit that we got from some company called National Toy Company, but that's the innards, that's the Regenaformer right there. That is the piece that they were able to create. So Browning Drake really did something. Well, National got into the radio business, and really this fellow, which I think is another really important individual in radio history, is James Millen. He joined National in 1927 as their chief engineer and their general manager. National created a long series of regenerative receivers, and here are some examples of them. They're short, the SW2, SW4, and SW3. This is an SW3 right here, shortwave receiver. The SW2 and the SW4s were kits. Those were kits. And then they came out with things like the SW5, which is another. These again, like I mentioned before, these are all pieces in my collection that I've collected over the years. This is an SW5, meaning 2 tubes, 4 tubes, 3 tubes, and 5 tubes. Now, we talked about superheterodyne receivers. There really weren't any superheterodyne receivers out there that, we talked about the ones from Western Electric. Those were very specific, produced for a very specific purpose. But for general shortwave reception, there really wasn't anything. Well, National was approached by General Electric. General Electric received a contract in 1932 from the CAA, the the Civil Aeronautics Administration, I think is what it was. CAA. It was basically the forerunner of the FAA, Federal Aviation Administration. That was the forerunner. They gave a contract to GE to establish air-to-ground communications at airports. Well, GE is good at building transmitters, but they didn't have any receivers. So GE goes to National. He goes to Millen and says, build me a receiver. So Millen, being the chief engineer there, designs this high-performance shortwave receiver called the RHM. Now, the RHM is a very high-performance 9-tube superhet. And I have one sitting over here on the shelf. It's really a beautiful piece of equipment. They were cumbersome, but that was the prototype. The RHM was the prototype. What he delivered to General Electric was something called the AGS, Aeronautical Ground Service Receiver. And this was really one of the first high-performance commercial superheterodyne receivers. Of course, what's happening at this time? We've got the Depression. So it really put these beyond the pocketbook of most everybody who playing in amateur radio. No one could afford these things. So they were really a very good high-performance receiver. There were roughly 300 of them produced, and I've had 3 of them. So I've still got two AGSs and an RHM, 2 different models of the AGS. But there were only 300 of them produced for the government for that GE contract. But they were just too darn expensive. So Millen says, "Hey, well, let's build an inexpensive version of the AGS, and we'll call it an FB7." And the FB7 Fun Box, FB. 7 tubes, it's a superhet, and it's very similar to the AGS, except it doesn't have the first RF stage. So here's your FB7 here on the left. That's the Funbox 7 with the plug-in coils. It's got 2 plug-in coils, and here's an AGS on the right. So it's got the 3rd plug-in coil. That's the first RF amplifier. So these were great receivers, but one of the problems with this receiver was, and the controllers, the radio operators complained about it, when they switched bands, you had to switch coils, and they'd get the coils mixed. Well, that was a problem. We'll talk about that some more in a minute. But really, one of the things I really treasure in my collection is this next guy. This is really the first production superhet receiver. This is the Hammarlund Comet. And I have one that has not been, it's all original. I've never touched it. It's in a beautiful walnut cabinet. It uses plug-in coils. It has a lot of issues. This was not a very long-lived radio. If it lasted a couple of months in production, I would guess that it probably did not last any longer than that, because it was replaced by something called the Comet Pro. It lacked a lot of shielding, so it had a lot of stability issues. The Comet Pro corrected that. But 1932, Hammarlund Comet, first production shortwave superhet that really got out to the general public for doing shortwave listening. I mentioned this guy a little while ago, James Lamb. Here's my defining moment number 8. As I mentioned, he was the technical editor of QST. And he, 1932 and 1933, he publishes a series of articles on receivers called What's Wrong with Our CW Receivers? June 1932. And I've got these articles, I've read them. They're fascinating to read because it's all stuff that makes sense today. I mean, I can relate to everything that he's talking about. And I talked about that early in the presentation, the things that James Lamb came up with. By August of that year, he describes something he called the single signal superhet. This is important. This is single signal. So the problem in those days was, when you tune around, you'd hear 10 signals at once, which is not acceptable. It's really bad. You hear 10 CW signals on top of each other. How do you decode that? How do you listen to that? It's really difficult. That's where this series of articles came up. So he comes up with this thing called the single signal superhet. One of the things that he described in his articles was what's called the processing chain of a superheterodyne. This is really how you set the gain of each stage so that you get optimum performance from the receiver. He defined this stuff in 1932 in QST. Pretty awesome. Stuff still holds true today, everything that he did then. He defined the architecture for double conversion, which is commonplace today. We use double conversion. Basically, basically a first IF and a second IF, so two local oscillators, different frequencies, followed by detectors and audio amplifiers. Just elegant simplicity in the receiver. And like I said earlier, these concepts that he defined in 1932 stand today. And Millen and Lamb collaborated on lots and lots of papers that they published together. These two guys were giants in engineers in those days. It just boggles the mind at the stuff that these guys came up with. Just really respect them a lot. I've got a lot of material that both Millen and Lamb have published over the years, and it's really interesting stuff. You've heard the term, and it's not ham radio outlet HRO, it's the national HRO receiver. Hell of a rush order, so it is said. The name HRO came from that expression that James Millen scribbled on a blueprint to get this thing out the door, to get it into production. The first one was delivered in March 1935. And the thing that made this receiver so spectacular was this thing called the PW micrometer dial, this little guy right here. If you think about the radios at this time, it was very difficult to tune them. They might not have any reduction gear. Well, you had the Velvet Verniers that gave you a little bit of reduction, but they were really touchy. The Velvet Vernier was a incredible gear reduction system that would take that band dial and spread it out into like 10 feet. So you're tuning across, let's say, like a couple of hundred kilohertz in 10 feet of space. So you can imagine how easy it is to set it to pick up a signal. It's very easy to tune. And these things are great. Now, the first one was delivered in March of 35. I have one of the HROs in my collection here. It was produced in April of 1935. So it's a very, very early model of the HRO. And these are just beautiful, beautiful receivers. Like I said, unprecedented tuning rate at the time. Totally resettable. You go right back to the same exact frequency. And this receiver used something different. You know, you saw the AGS with the plug-in coils. This uses plug-in coils, but he took the coils and put them into a box so they were all strapped together. So you couldn't put them into the wrong place. You couldn't pick up the wrong coil and stick it in the wrong place. So you had a plug-in coil box, and I'm sure folks have seen those. It also had an external power supply. One of the things that Millen felt was the power supply shouldn't be in the receiver because it created too much interference and noise in the receiver. So it was always a separate box that was away from the receiver. This product line started in 1935, continued until 1964, which is pretty amazing. So it consisted of the HRO Junior, the HRO5, HRO7, a bunch of other stuff, HRO50. The last one they produced was the HRO60, and just a really interesting product line that led through. I wasn't really going to talk about this stuff now, but this led into World War II and the HRO was an asset in World War II. So here's the HRO. And I like to say this is Millen's embodiment of Lamb's ideas. It was really considered the cream of the crop. That's not my opinion. That was the opinion at the time, that it was the cream of the crop. So this is that early HRO from April. And you can see the PW dial and national company. There's the coil box. There's the power supply in the back. And these little coils plug in here. And one of the interesting things about these early receivers that you'll notice is there's no nomenclature a lot of times. You don't, well, what does this knob do? You have to know what that knob does. A lot of times it's just printed on the knob itself. In the case of this one, it's on the knobs themselves what they are. So there's like a volume control and a filter and things like that. So that's what that is. So again, this was an expensive receiver for the amateur community. You needed to have something that was a lower cost. So Millen said, well, let's build this version of it. This is the HRO Junior. There was a low cost version of that receiver that does away with the with the meter and gives you one set of coils, and it was $100. Now that was a hell of a lot of money in 1935, but $100 right there. Power supply, one set of coils, and you got it. Well, people got tired of switching coils all the time. A lot of receivers you had to switch coils in. So one of the things that National came up with in Millen was this band switched receiver, and it basically took all the coils and put them together in that coil box, and then the coil box just slides back and forth, and there's a row of contacts that connect to the coils, and you see which band you're on by seeing this little white dot through the little hole there. And this is a general coverage shortwave receiver, 1937. That's the 100X. 100, the 100 means that it's a general coverage shortwave, and the X means it has a crystal filter in it. So they did a whole series of these receivers, and that basically Millen maintained his ideas and the things that he had set out to do in the embodiment of Lamb's ideas. The one thing he did do is he put a power supply in the receiver. That was important to get that thing as a single unit, so you didn't have to have other stuff dragging along with it. But he was able to isolate the coil sets. He maintained that ideal in this thing. He used the PW micrometer dial, but his departure was having an internal power supply. But he figured out a way to shield the power supply so that you didn't have interference from that power supply in the receiver. So this is an important radio. Different versions of this, NC100. Like I mentioned, 100 denoted the general coverage. There was a 101, which was ham bands only. And you add the X, it had a crystal filter, so you get a little bit better selectivity on it. So these were the radios. Now, another one this is one that I like, and this is Dennis opinionating on this one, but this is a neat receiver. This next one is the SX28. A lot of folks own these. Maybe a lot of you have used them. Maybe some of you own them. These are just a wonderful receiver, and it's just a Hallicrafters. It is really the epitome of Hallicrafters in that vintage, around late 30s, early 40s. Just a beautiful piece of equipment. But I'll mention some other notable receivers from that time. And the reason I mentioned these is I'm a Southern California kid, so I'm going to talk about companies from Southern California. But some of the guys local to LA are companies like Breing. Breing made some marvelous receivers in those days. Patterson is another one. I have a Breing 14 in my collection, which is a beautiful, beautiful receiver. Patterson, Gillifan were all local to the LA here in Southern California. The Breing, they made a bunch of high performance superhets, the Breing 9 and the 12 and the 14. And the 14 is 14 tubes with 2 RF stages of amplification. So more's always better, right? These are really pretty radios, but there's my Breing 14. That's a picture of it. I've got that in my collection, which is a neat little receiver. All right, so that concludes part 1. Let's talk about what I'm going to talk about next time. What happens in part 2? Well, of course, what happens in the 40s? We get into World War II. War tends to advance technology very quickly. We know that. One of the big things that came out of World War II, of course, was radar. That was the big advance. But a lot of widespread acceptance of single sideband, we know about that. Other modes like, we'd used AM up until now. FM became popular, sideband and CW. We know about all of those. We're going to introduce the transistor. We're going to talk about some other introductions of vacuum tubes, but we're going to talk about the digital age and maybe talk a little bit about the future, what's in store in the next generation of receivers. But that's what you can come back and see in 2 weeks. So that's it from me. And we're open to questions and comments at this time. And I will return this to normal. There we go. Dan or Barry, I hope you're there.
We are here. We are here.
All right. So I will entertain any questions and I will try to answer them. If I can't, I
remember the very faint smell of those old radios.
Oh yeah, you know it. You know it. Let's see.
And they also used dry cell batteries.
Yes, they did, and wet cell batteries too, which were dangerous. Power supplies were pretty rare, uncommon. You'll hear something called a farm radio. That's a term that was very common. It was a farm radio, and that was all run off of batteries. And so you'd have to take, using wet cells, you'd have to take your wet cells into town and get them charged and then come back and run your radio. Yeah, the HRO complete set, you're right. The complete set with all the coils and everything, you would push $200. That's right. That's why they had the that junior was really really. I've got that picture is actually one in my collection that's over here on the shelf too. Is the junior.
Having known a bunch of dairy farmers back in North Dakota, farm radios were fairly consistent business by people that came through and rebuilt old 5-tube superhets.
Yeah.
Because the music on the radio kept the cows quiet and content while you milked them. Otherwise, anything noise or anything or a dog coming in would scare the cows. It'd stamp their feet and either hurt the farmer, spill the milk, or quit milking. So the farm radios were not just for entertainment.
Yeah.
Let me throw one more thing in. I had the call letters KE2XFG in the 70s. I had a satellite experiment with NASA, and I was assigned a series of experimental calls for all the stations. So they still use that, the X da 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 and the suffix of a call.
Yeah, those are still used today. That's right. Absolutely. Yep.
Yeah, they used to have the farmer port on the radio that almost every farmer in the area.
Yeah. So, Doug, you're talking about a 2-meter Regen transceiver. Somebody mentioned about a Heathkit lunchbox. Was it a lunchbox? But no, it was before that.
No,
1961.
it was like a Motorola handy talkie, a luggy talkie that somebody built, and it had B batteries and A batteries and a telephone handset. But in the inside was about a 4-turn coil and a capacitor that attached to the top, and a 3A5. And so it transmitted while it received and received while it transmitted. It was, I got into W6NLZ's radio while he was trying to set the record with Hawaii, and I was told in no certain terms to get the damn thing off the air. Or they'd come after me, so I junked it. But it was
actually, in my collection, I've got something that National produced called a TRW, which was a transmitter receiver in a wooden toolbox, TRW.
Okay.
And I've got 3 of those. One is awaiting restoration. The other 2 are fully restored and operating. And that was from the 30s. And those were 6 meters. And they were the same kind of thing. It used a single tube. It used 2 tubes. One is an oscillator and another one is an audio tube. And you basically used it as a regenerative receiver or a transmitter. And you used you had it was 2 tubes to make that. I don't remember what the tubes are, but yeah. The good old tour. Yeah, I just recently got rid of a tour that I had. I gave it away.
I wonder why. Well, actually, I had one too. And back in the day when they were cheap, they actually worked. They were crystal controlled, and you could talk to your buddies if there were other buddies around on 2 meters, and it was okay.
Yeah.
You could FM them though. Just get real close to the transmitting oscillator and talk real loud at it, and it would FM pretty well.
FM. Yep.
Frank made the comment $200 in 1930 is equivalent to $4,578.
Yep,
wow,
that's right. Well, think about what a high-end, you think about that. That was a high-end radio. Think about what a high-end radio costs today, like one of the Yaesus or the Kenwoods, the top of the line Kenwoods. You're right in line with that. They're thousands and thousands of dollars today. I look at things like when the 7800 came out, it was like $8,000 for an IC 7800, and it's like, God, that's a lot of money. But then I started looking at things like a KWM2A, what it would be worth today if you were going to buy that radio today, and it's in the same ballpark. So it's like, it's what's your dollar worth, and the technology changes, but you get a lot more bang for your buck today. That's for darn sure. Yeah, K4D, yep, 6,000.
And
6,700 gets up there. Oof, not cheap.
They built their own receivers.
Say again, I'm sorry.
They had to build their own receivers.
Oh, absolutely.
And that's how the AM radio stations. You had to, if you wanted to listen to the Shadow or any of the radio stations.
A lot of people built.
That's when my grandfather used to write a weekly radio column on how to repair superhets and all this, and how to do stuff for the Boston Record.
Wow. One of the fun things is looking at some of the old radio magazines. I've got quite a collection of in my historical collection here. I've got lots of old publications and lots of old magazines and old books on radio, and it's fascinating to go back and read some of those things. Really enjoy that. We were just looking at I was showing Lisa last night my first edition of the ARRL Radio Amateurs Handbook, which is amazing. That was published in 1926. And I've got a first edition and a second edition in the collection. They're just really a neat book. If you've never had an opportunity to read some of those old radio books, I urge you to do so because it's a lot of fun. And you learn a few things, you learn about how things were, back then and how they evolved into where we are today. So it's really neat stuff.
I got a crystal set a few years ago with a variable coupling, and I occasionally put it on the air. I put it on the one side of the coaxial antenna or something and get a wire out. And it's interesting to go and see what life used to be like with just a crystal radio.
Oh, sure.
That changing the coupling and tuning the capacitors, and you can settle in on a station. In the daytime, in LA, I get about 4 or 5 stations. And with my earphones on, and I remember those days when I was a kid, when I had a Philco crystal set, a little red box. Anybody have one of those with a wiper that went back and forth and a little Galena crystal? That takes me back to those days, and it's kind of nice to do once in a while. But then I'll go back to my my K3 and forget all about it.
Dave, you're right on the Rode and Schwartz. Oh my gosh, we've got a few of those around here too. A couple of Rode and Schwartz receivers. But yeah, those things their stuff is astronomical prices.
You're going to be opening up your house for a tour here pretty soon, the way this is going.
Well, we did one. We did the one on RATPAC here a couple of months ago, you remember? And people are asking for me to do that again.
Yeah.
Some other folks to do it. And hopefully in the next few months we'll have the rest of the ham shack finished. We can do a tour of that too, when everything's all put together.
Dennis, should we have a dual open house and link it up with OVRO and get people up the trail?
Oh, that'd be cool. That'd be cool.
Yeah.
Well, hang on a second.
Up the road.
If you have tours, you have to charge.
Lisa says, if I have tours, I have to charge admission. Gotta pay for this stuff somehow. Yeah, that's it. Funny stuff. But let's see, what else we got here? Looking at other comments here. Oh, yeah. Interesting comment about farming. Let's see.
They put the Alexanderson units on the air once a year, I think, in Chatham.
Nice. They still have, do they still have the alternators there and they put them on the air? No.
Station there.
There's just a station there. They had 2 of them. Yeah, the coastal station here in California, KPH up in the Bay Area, Marconi actually had a transmitting site there. Where's the location? It's just south of where they are on Point Reyes. But Marconi had a station there as well and used Alexanderson alternators. All that's left of that station are the bases, the footings of the towers that he had, and I think the foundations of the Alexanderson alternators. But I will tell you, here's a claim to fame of yours truly. I mentioned SAQ in Sweden, the only operating Alexanderson alternator in the world right now. And they put that on the air sometimes a couple of times a year. They do it on Alexanderson Day, which is celebrating his birthday. And they also do it on, it's either New Year's Eve or Christmas Eve. I think it's Christmas Eve they put it on the air. I was the first person ever to be able to pick them up on the West Coast of the United States. And that was right here where we live right now, is where I picked them up some years ago using a what you can consider a software-defined radio in the early days of it. And I sent a reception report to them, and they were just absolutely blown away. The fact that I proved to them that I had received their signal, and they had a special write-up in their when they did their report after the fact. You know, they're talking about all the people, all the reception reports that they received, and they talked about the reception report from me here in Inyokern in California, which I thought was really cool. So it's been done many times since then. It is difficult because they transmit down around 17.2 kilohertz, and they're transmitting with about 200 kilowatts at that frequency. You know, think about that. That's a very, very low frequency. Think about what the wavelength is at 17.2 kilohertz. It's big. So trying to pick that signal up over here on the other side of the world is not trivial, but that was fun. Anyway.
Okay.
Oh.
This has been a lot of fun, folks.